I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Taylor Sparks, and I'm joined by Andrew Falkowski and Jared Duffy, our audio guru, and we are so excited to bring you episode number 35 on spark plasma sintering. I promise we didn't pick this just because it has a rad name and because Naima is Sparks too, but it kind of did feel right a little bit. So, what's been going on, guys?
Last week we put out a micro episode on cooking. We thought that it was rather fitting. I've been doing a lot of cooking myself, and so I was thinking, right, I grab my vegetables and I go to the cutting board, I'm cutting them up. What's involved? Like, does it matter what cutting board I use? Does it matter what knife I use? If I cook it in a copper pan versus cast iron, does that matter? That episode tries to answer those questions, so check it out if you haven't already.
All right, I have to announce something. I haven't listened to it yet because I wasn't on that one, and I've been busy, but I will listen to it this week, and I'm psyched to learn all about cooking materials.
I also have only listened to part of it because, if you look now, you can see Ramsey's in the editing notes, which means he shoots me over some notes, I edit some things, and so sometimes it means that maybe I missed the point of some podcasts, but I get around to them sooner or later.
Well, teamwork makes the dream work, guys.
Yeah. Also, because I'm technically I work for the school. This is for anyone here who works for schools. If you didn't know this, you're eligible to get a COVID shot. So I've got my first vaccine in my arm.
So you're saying the Materialism Team is now 1/4 safe from zombie apocalypse in case the rest of us all die. You're going to carry on the tradition.
1/2 of 1/4.
1/8 of the way protected.
Yeah. So
that's a start.
It's a start.
I'll take it.
Yeah, we're getting there.
Okay, well, we're pumped to be bringing this episode today. It's a snowy winter's day out here, but we're going to talk about a red hot topic, which is sintering. Andrew, get us started. What on earth is sintering?
This is a term you'll hear a lot in metallurgy and ceramics, and it refers to the ideal processing, not the ideal. It refers to the general and main sort of processing that they use to make these. If you think about ceramic materials, right, these are a bunch of carbides, nitrides, oxides. These have incredibly high melting temperatures. If we were going to treat them like metals where we melt them into a liquid form, it's going to be very cost prohibitive. The equipment's going to be expensive. It's also very dangerous. So the idea behind sintering is to say, okay, maybe we don't need to completely melt it into a liquid. Maybe we can just merge the particles together via local melting.
Yep. This idea kind of springs out of the field of metallurgy too. It's not just ceramics have done this, powder metallurgy. So making your part and starting with powders, like particles, is kind of the idea here. So one of the big things that you have to achieve in sintering, like pretty much the main goal, is to remove porosity, right? You've got little particles and they have their junctions where there's big voids. How do you get rid of those, right? So confession time. I've been teaching material science for a long time, and I knew this was true, but it's like I forgot it. When I talk generally about why things sinter, what's the excuse that I've used? What's the explanation? I've said for a very long time that it's driven by, well, obviously, a reduction in surface area, right? And it's not that that's not a driving force. In fact, let's take a look at it. When you have lots of surfaces of energy, and so obviously that's going to not be in favor of having those surfaces. And if you get rid of them, you go down in energy. So yeah, it is a driving force. But is it a big one? No. You can look at actually the equation for it, and it's 3 times the surface area, right? The surface energy, divided by the particle size times the density. So plugging in some realistic numbers for, say, a ceramic system, even a really small particle like 100 nanometers, which is small, you're only looking at an excess energy of 10 joules per gram. So to put this in comparison with the driving forces from, say, a chemical standpoint, that's tiny. Those are kilojoules per gram. So that's not really the big reason. So what is the big reason is something called capillarity, right? Capillary pressure. When you've got these curved surfaces that come together, like at the junctions of these particles, at those regions of high curvature, you can generate some really big pressures on the order of like a megapascal. So all of a sudden, you get this compressive pressure that's allowing you to densify these materials right there. Obviously, that is small compared to the pressures that we can apply to something, right? If you squeeze on something, 1 megapascals, that's a cinch, right?
Yeah, they're typically up. I mean, in just a general case, I get near 3 megapascals, I think.
100 megapascals is pretty typical. In any case, we can go far beyond capillary pressure when we apply an external stress. So So it's not like you have to have a stress, but boy, does it help. If you can squeeze on something like in a hot press where you center it in the presence of an applied pressure, you're going to do a lot better.
Yeah, I mean, it makes sense intuitively as well, right? Even just think about snowflakes, right? If they come down in kind of a powdered form, right? There's voids in between them. But if you go and you compact them, you're going to make it denser just by forcing the particles closer together.
Absolutely.
Now you add heat and allow them to plastically deform. You're going to be able to pack them even closer.
Yep. Okay, so how does this process happen? It involves diffusion, right? So if you got these particles in there filling the voids between them, then you have to have mass like moving through material. So mass transport, we call that diffusion, right? But there's different ways that it can happen, right? You could have mass moving through the bulk of the material, moving along the surface. It could be vaporizing, going to the vapor phase and then recondensing. And so all of these things can and do happen. It's just that some typically dominate depending on the conditions of your experiment. And if you're looking at this from a utility standpoint, you actually want some to happen more than others, because in these different scenarios for diffusion, the source of matter is going to be different. The sink is always the same. It's always going to go to this neck region at the point where the two particles come together. But the point where the matter comes from, whether it comes from the bulk of the material along the surface, will dictate the type of porosity that might get left over when you're done. You might be left with little tiny pores that are just really hard to get rid of. So in fact, there's a well-known phenomenon that densification actually slows down as you're getting closer to the end. So it's easy to get the first gains, but man, to get that last 1-2% is really, really challenging. It goes really slowly. What you're hoping happens is that you get mass diffusion along the grain boundaries. The grain boundary leads to the pore, so it's able to keep on pumping material to that pore to fill it up. But what can happen is that your grain boundary can grow and actually move past the pore. So now the pore is inside your grain, and now you don't have a good vehicle to get material there. So it slows it down, and in those cases, it's really hard to get rid of those pores.
Right, and as you're adding more material, now your gradients are changing as well. And so diffusion is also going to be affected by that.
Mm-hmm. Now, because you're filling in these empty spaces, you end up with something called shrinkage, right? So in ceramics, these things shrink a fair bit, like 20%, which is wild. Imagine that you're making some custom gasket, right, for the spaceship or something, and you have to take into account the fact that when you make this, it's going to shrink 20%, and add on to that the fact that ceramics are really hard to machine afterwards, so it might not be trivial to get it the right shape. You can see why net shaping ceramics is such a challenge and why understanding sintering is really pretty important.
And this also goes into why you'd want to have precise control over the processing conditions as well, right? If your temperature gradients aren't even, you're going to get uneven shrinkage as well. So you might plan your mold or your why am I blanking on the word for
your die?
Your die, geez. You might plan your die with 20% shrinkage in all directions evenly, but if your heating element isn't even right, you're not going to actually get that, and then you're going to run into problems.
Another something that, people, if you ever work with ceramics, you'll realize that they are like super anal about controlling the powder and all these pre-processing steps. But the reason why is you get what are called these agglomerates, hard or soft agglomerates. Think of these as regions where your powder particles have sort of already condensed together a little bit. So now imagine the overall body starts to sinter, but some little region has already sintered. So the stuff that wants to sinter uniformly can't, because that region is already sort of collapsed into a higher density region. So this causes cracks. I can't tell you how many ceramic samples, because that was my background before I went to grad school, and in grad school was a lot of ceramics. So many samples broke, probably because I just had hard and soft agglomerates, meaning I just didn't have good powder control. So sieving, controlling particle size, these are really important things to make sure that your particle doesn't crack due to problems with sintering.
Yeah, in my experience with working with ceramics, I see them all the time. There's a lot goes into the science of getting the right powder distribution and using things like dispersants to prevent that.
So now we've talked a little bit about sintering, at least the basics. Let's say a few words about grain size and then scattering. So grain size, obviously, as you sinter something, you're going to grow these particles together and you're going to form grains, right? In fact, even within the particles, you could have multiple grains there. Now, there's something that is kind of sad about the state of the world, and that the big get bigger and the small get smaller, right? Big economies, big companies swallow up small ones. It's kind of the same thing with grains. Little tiny grains get swallowed up, they get dissolved to grow the larger grains, right? If you've been a material science student for more than like one day, you've certainly heard the ice cream analogy, how grain size, Ostwald ripening is ruining your ice cream. It's a little more complicated than that. It is, but it's really like a phase separation going on there. The water and the cream are separating. But in any case, things grow over time, okay? So why? Here's the question. Why on earth should they grow over time?
Well, it has to go back, right? maybe the minimization of surface energy doesn't explain sintering, but it does explain the grain size here.
Yeah, and the mechanism is actually pretty cool. If you look at a really small particle, it's got a really large radius of curvature at its surface compared to a big particle. A really big particle looks basically flat on the surface compared to a small one.
Yeah.
And what you see is that the solubility of these atoms, of the materials, changes as a function of that radius of curvature. So a small one has a higher solubility. So literally, it's dissolving into the material around it because it's more curvature. Whereas the big ones has lower solubility, so it's plating out, it's depositing there. And so you see these things dissolving away and forming on the surface that's larger nearby, which is pretty cool.
And it really comes down to just the energy requirement of a surface relative to your volume.
Yeah.
And it's like if you have a larger, more bulk material, it's easier to maintain a surface.
Yep.
But if you're smaller like that, these smaller grains, it's much harder. And so in sintering, it's all about trying to control the ripening of grains and what the distribution of those sizes looks like.
Now, the last thing we're going to say before we get into the SPS topic itself has to do with scattering. So scattering, you can scatter lots of things. You can scatter light, right? You've probably seen like an old foggy pane of glass where that light is not transmitting all the way through. It's getting scattered, and so it looks sort of cloudy. But you can also scatter things like phonons, right? Heat, right? These lattice vibrations that carry heat, they can get scattered, or electrons or holes, right? Lots of things can be scattered. What causes the scattering is oftentimes impurities and defects, grain boundaries, missing atoms, all sorts of things can cause this. And since those things have different sizes, you can get interesting size-dependent scattering. So let's consider the first case where you have something really big, a big scattering defect where the object doing the scattering is significantly larger than the wavelength of light that's being scattered. In those cases, you get scattering that's basically the geometric shape causes the scattering area. Okay. So think of like the double slit experiment would be an example of that. Then you can have other ones where if the scattering thing is about the size as the wavelength, this is called me-scattering. And in that case, the surface properties of the particle doing the scattering can dominate scattering. And then the last one is Rayleigh scattering, where now in this case, the thing that's causing the scattering is smaller than the wavelength. So this is why the sky is blue. You've got all these little tiny particles in the sky, in the atmosphere, which are smaller than the wavelength of light. And then they all emit that light. They re-emit the radiation, but they do it incoherently because a bunch of small points do it all at different positions, and so it's no longer coherent. It gives that sort of nebulous sort of haze. So obviously I gave you light examples, but you can have this also happening with heat and electricity. And so scattering, maybe you want it. Maybe you want to scatter things and you want to inhibit maybe heat transfer, right? That would be like for a thermal barrier coating. But oftentimes we don't want scattering. And how does this tie into SPS? We'll get there. All right, let's first dive into the history of SPS.
Sintering as a practice has been around for going as far back as 6000 BC. Ancient Egyptians were sintering metals and ceramics as early as 3000 BC, and the Incas used it to make jewelry in South America as well. And if you think about this, it makes sense, right? Back then, even with somewhat primitive technologies, being able to melt even things like metals, even softer metals, was going to be difficult. So with sintering, where the temperature requirements are much lower, you're still able to achieve a dense solid without having to fully melt it. And this allowed them to produce much of the artifacts in terms of jewelry and pottery that we see today in many museums.
Yeah, absolutely. In the more modern era, actually only 100 years ago, which blows my mind, right? In 1906, a guy named Arthur Bloxham, he's an English scientist, he was starting to use DC current to actually do some sintering. Basically, he realized as you pass current through stuff, anybody who's had an old electric stove knows that as you pass current through it, it heats up, right? That's joule heating. And he realized that as you do this, you can actually get things to consolidate and sinter a little bit. Now, he was literally touching the ends to it, it seems like. This wasn't like a confined system with a die. It was just passing current through filaments and having them sort of solidify under the current. So it's not SPS as we know it, but it was kind of a start because they're using current for the heating. What was the next step?
The next major innovation comes in 1912 in a GE patent from George Weintraub and Harold Rush, which focused on refractory materials, but this time they were adding pressure. This was, I think, the first major patent for this technology. There's a great illustration within the patent of how it works, so we're definitely going to put that on our social media so you can check it out.
Honestly, it looks pretty similar to the designs that you see today for SPS process. It's pretty close. So our next innovation comes 1922. It's Alexandre Duval de Adrien. He's a French guy living in Washington. And he realized that, holy cow, when you take these metal oxides, you can heat them up. And once they start glowing red, they are able to conduct electricity. Right nowadays, we understand that. That's just like an insulator. It's a wide bandgap insulator. You heat it up enough, and eventually you'll hit that intrinsic region where the carriers get across and it becomes conductive. But he realized, great, once it gets hot, if he heats it up with some sort of regular technique, then he can pass a current through it to get it to sinter the rest away, because it goes to really high temperatures, 2000 plus Celsius.
Yeah, and they typically do this with graphite. It's just a really it's very susceptible to inductive current, and you can really
induction
heat it
furnaces, even microwave furnaces. We had an episode about this where I actually talked about that, the role that carbon plays. But once you get it hot enough, then your material is a susceptor, which is pretty cool. The next innovation comes in 1930, and this is the one that all of a sudden is looking very similar to the modern day tool. In 1930, George F. Taylor, again at General Electric, bringing the hits. The key innovation is he did what had been done before, but this time he put it in a vacuum chamber. So he could either pull a vacuum or put inert, like hydrogen or whatever atmospheres. So all of a sudden you can make things that would otherwise be oxidized because they're high temperature. What he worked on was our old friend, cobalt bonding tungsten carbide, who we know and love. And the other innovation that he did here is that the conductor housing this powder the dye housing this powder was a conductor. So when you apply the current, even if a bunch of the current goes through the dye, it's still going to heat it up. It doesn't matter if your powder is necessarily conductive. Now you had a way to sort of confine it, apply pressure, prevent oxidation, and get it to heat up even if it's not a conductor, which is basically what we're at today.
Yeah, later in 1962, a Japanese scientist, Kiyoshi Inoue, described a sintering process for metal particles using an applied pressure, so pretty similar here. But this time, he describes this idea of a space discharge occurring between the particles, so something like a plasma, and basically turning into an electrical spark. And this kind of kicks off this, what I think is a misnomer.
Yeah, call it what it is. It's a misnomer,
It's a misnomer. It's they call this the spark plasma sintering method. But we'll get into why that's probably not accurate. But it was believed by Inoue that this spark causes partial ionization of the powder at the various points of contact.
Therefore, plasma.
And thus, so with the simultaneous application of pressure and the concentration of heat, you get interdiffusion, and thus you get this fusion that we're looking for in sintering.
Okay, so this happened in Japan, and it really took off, right? In Asia, a bunch of small companies started making these presses because they're really handy. Whatever's going on inside, it was a bit of a black box, spark, plasma, or no. It's a useful tool. And so in the 80s, small units are available. In the 90s, you start getting large units that are using huge currents, 20,000 amps, some of them, which is bananas. And then you get companies like Sumitomo, right? Sumitomo Heavy Industries, they're the ones who made the Dr. Sinter tool, which I used way back as a graduate student. It's huge. It's like the size of a room. It's this massive tool, little Dr. Sinter on the top of it.
Wait, despite the size, how big of a part can you make with it?
So that's what was funny is this tool, at least the early one I used way back then, was massive. And the biggest part we could make would probably be like 2 inches. And even that would be like probably really you end up with non-equilibrium process because it's so big that there's big temperature gradients. So realistically, the vast majority of parts that come out of it are like half inch, maybe an inch. So yeah, it's a big tool. Nowadays, you can make them smaller, but that's where they were at back then. Now, one last thing to differentiate is you might hear flash sintering thrown around that term in material science, especially in the ceramics industry. Flash sintering is not necessarily the same thing as SPS. There's some differences. Flash sintering was developed at Colorado Boulder in 2010, and the key difference is basically how long you apply the current, right? So this pulsed electrical current that causes the sintering, if you're doing what's called ultra-fast sintering, then that current is only applied for like 0.1 seconds, which means that you're not using traditional power sources. You're using capacitors, capacitive discharge, right? Flash sintering is kind of in the medium region where you're applying the current from maybe 0.1 seconds up to 60 seconds. So it's short term, typically higher voltages. And then SPS is typically over 60 seconds, but still not that long. Okay, so those are kind of the three terms, ultra fast, flash, and SPS. And then one last thing I thought was interesting, there was a conference kind of on this specialty sintering technique back in 2016, and they did a survey, and they think that there are about 3,000 of these presses in operation. So it is certainly popular. I can tell you by reading, I read the scientific literature all the time, and in my fields, the ones I work on, say thermoelectrics, holy smokes, everything is made by SPS nowadays. It's an extremely popular tool for making polycrystalline samples.
And it's a huge topic too, right? They had all these ceramics that they had made, but then with the power of SPS, as we'll get into, they were able to take those properties even further.
Yeah.
There's thousands of papers written about this alone. And so it's an important topic in metallurgy and ceramics, and rightly so.
Okay, we're going to take a quick break and talk about our sponsors real quick, and then we'll be right back with some more info about how SPS actually works and some of our experience actually building an SPS press in our lab.
if you've been listening to the show for a while now, you've known that we've had MatMatch as a sponsor for a while, and that's because they're great. They're a company that's passionate about material science, and their goal is to help connect materials engineers with materials providers and suppliers. Their platform is used by over 1 million engineers each year, and best of all, searching for that perfect material is completely free, and it's also really easy. If you go on some of the comparable ones like Sigma Aldrich, it takes like a minute.
Brace yourself for cringe.
Yeah, it takes like a minute to actually load the results. If I go on MatMatch, it's almost instantaneous. It's a really easy searching experience. Head over to matmatch.com, check it out. It's even kind of just fun to go and explore all the different options they have and see how you can compare the properties across each option.
Our podcast is also sponsored by Materials Today. Visit materialstoday.com to stay up to date on the latest happenings in the material science field. You can read some of their fantastic articles that they've published. For this episode, we've actually found a cool one on SPS. Take a look at it. You can also head over to elsevier.com to find out more about their other journals, their books, conferences, and related programs. Okay, so SPS as a tool is so valuable that when I was in graduate school at UCSB where I started, we didn't have one. And when we switched labs, we moved to Harvard, it was so great that we actually wanted to build one ourselves. So for the first time I saw how these things are built, and I realized it's not like rocket science. It's a load frame that can apply a pressure. It's some sort of chamber that can, pull a vacuum on it. You have to have it conduct electricity. So this is the trickiest part, is the load frame pistons that actually squeeze your material have to be the source of electrical conduction. So you have to pass the current through those, and then you've got a power supply. It's a little more than that, but that's basically it. So I saw that built, and then when I became a new professor, I actually commissioned my grad student Jake to build one, and it was actually a couple undergrads helped him first, and it was a heck of a job. It was way harder. We saved some money for sure because these cost about $250,000 to buy, and we did it for probably half of that, but it was no walk in the park. It was a fair bit of doing. So we're going to post some pictures. You can see Jake and his creation, Gary, our SPS, on the Instagram. It's pretty great, but let's dive into a little bit more of what's going on inside of an SPS.
Yeah, absolutely. I think it's helpful to kind of break it down into the stages of sintering, and then we can kind of talk about why each of those come about.
Okay.
So first off, we have our sample in the conducting die. We want to pull a vacuum. We want to get rid of any oxygen that's going to oxidize in our sample under this high temperature environment. The next step is we're going to apply that pressure, so get everything nice and condensed. Then we'll use Joule heating to apply the heating. And finally, we cool it off, right? That's the overview of kind of what's happening. And the reason they do all this, and the real key advantages of SPS are really we're able to achieve lower sintering temperatures, which lowers our cost and makes it a little less dangerous.
And that's mainly because you're just squeezing on it, right?
Yeah,
if you do
absolutely.
pressureless sintering, you have to go to higher temperatures. But if you're squeezing on it, you can cut it by several hundred degrees.
Yeah. If you, with increasing pressure, let's just say you wanted to achieve like 95% density or relative density. As you increase the amount of pressure, you can apply lower temperatures, which reduces your cost and also makes it a little easier.
Then the other thing is how quickly it can happen, you mentioned. That's a big advantage. What we found is that oftentimes we would sinter things in 10 minutes, 5 minutes. It actually took way longer to get this thing to cool off. We spent almost all of our time waiting for it to cool off because think about it, you've pulled a vacuum on it, so you're not relying on convection to cool it off. It has to conduct the heat from that. It was maybe glowing white hot when you sintered it, and that has to be conducted out through the pistons to your water cooling system, so your chamber has to be water cooled. It's actually a relatively slow process. It would take sometimes 2 hours for things to cool down to the point where you could actually touch it. Maybe you could cool it down a little bit in maybe an hour, but it might still oxidize. So it's funny that it's a fast process, but the cooling down step is what's killing you.
Yeah, and even that has some problems, right? Because if there's still heat there's still going to be some diffusion, which they want to avoid, right? One of the main advantages is that you can achieve, because it's so short, you can achieve much finer grain structure. We'll get to that in a little bit. But let's talk about that misnomer for a second, right? They're calling it spark plasma sintering. Is it actually there? Maybe.
Yeah, I mean, I'm very skeptical. There's been a lot of research on this because as the name came out, people got, I think, bugged by it because they didn't think it was there. So then they set out to either try and prove it or disprove it. So what studies have there been done, Andrew, and what was sort of the outcome of those studies?
Well, I actually don't know any by name, but...
Oh, but still.
Okay, yeah. A number of studies have gone about applying different methods, adjusting the field to try to pick up any sort of detection. And over the years, it's kind of been this back and forth thing where a study comes out and they're like, we have definitive proof, we found it. And then someone's like, no. And then
Lies.
Yeah, and then another article come out. It's like, okay, this is a much more comprehensive understanding. We're pretty confident in this. And then it's like, nah. And so,
And this is specifically referring to like the spark and the plasma.
the plasma.
I
Nobody's
think
doubting
there's-
that the
like the
process
electrical
exists.
current. Like first off, joule heating, no one doubts that. But there was a question as to whether, like, okay, if you're flowing electrons, say one direction, is that going to influence sintering? Are you going to create the so-called electron wind, which will sort of carry mass along with them in that same direction? That seems a little far-fetched. Evidence doesn't really support it. If you look, and the key experiment I remember was one that alternated the current field, right? And when they found that when they pushed it just one direction versus like alternating it back and forth, you got the same microstructure. So it doesn't look like it's changing the microstructure with the direction of the current.
Yeah, it was growth with molybdenum silicon.
Yeah, polysilicide.
Yeah, and there was no change in the growth that occurred. The one explanation that people kind of use to say, like, okay, let's meet in the middle, is that with conductive samples, so metals or ceramics that are going to conduct electricity, you can get some plasma formation and sparks between the particles, but as soon as you get any formation, once they grow
press
together, no, it's not going to happen. So I don't think you need to believe in plasma to actually understand or benefit from the process, and I think it's still up to debate, but it's looking pretty slim.
And it probably, it's funny, we're going to name this, we've named this episode Spark Plasma Sintering, but a better name for this technique, there's a couple out there. One is called field-assisted sintering, right? An electric field causes it to sinter. Another one is pulsed electrical current sintering, except that you don't have to pulse your current. You can just do a common DC without blasting it on and off. Another one is electric current activated or assisted sintering, ECAS. So any of those are probably better terms for what's going on, but certainly the most common one in literature is SPS.
Yeah, just while we're still on this topic, let's dive into the three aspects of this and why it seems to be better than traditional sintering. So the first is pressure. We've talked about this a little bit, but the applied pressure affects the particle arrangement. It can rearrange and pack them denser together. You also get agglomerate destruction. So we were worried about the particles getting together, but by applying that pressure, we can break some of that up.
You get significant plastic deformation. That's another thing with shrinkage, right? Normally this thing would shrink when you sinter, and now the dimensions don't match. But if you're squeezing on this in a die and you're plastically deforming it and it's causing it to flow, you can make it match the die diameter, which is pretty convenient. It's a pretty big advantage.
Yeah, you can mitigate some of those. The other interesting effect you get is you can reduce the grain size of the sintered product. They found that by increasing the pressure, they get a somewhat linear relationship between decreasing grain size as well, which is ideal.
I'll say from a practical standpoint, having used SPS as a bunch, it's kind of a nightmare because you don't know the temperature inside of it. Like, how do you monitor the temperature inside of a die when the electrical current is causing it to heat? So what they'll do is they'll drill a little hole in the die from the side, and then they'll put like a pyrometer focused on that hole. That's one way to do it. But again, that doesn't go all the way inside. That's like a few millimeters from the hot spot. So it's a guess. You can put a thermocouple in there, and it's the same thing. But actually measuring the temperature is tricky. Some systems, like there's a German tool out there that lets you look down the piston onto your sample, like looking at it from above, basically. But there's not a great way of knowing the temperature. So you're never totally sure what temperature your sample's at. You could embed materials inside of it as a calibrant. I think there's been some work in that area, but it's a bit tricky.
They've done some simulations. So, right, we know that we know the heat capacity, we know how much joule heating is being generated, but right, it's not as simple, right? You can't just say, oh yeah, we measured the outside of the
we heated the sample to 1000 C. It's like, well, our thermocouple, which was 5 millimeters away from who the hell knows what was going inside the die, was at 1000 C. Where you see this happen, with the problem with this is that when you actually go to make things, you think that you're near the sintering temperature, but then you take it out and you realize that all that stuff that you were sintering actually got liquefied, and it squeezes up into the sides of the die. It's called flash. When it melts and basically gets ejected along the sides of the die, it destroys your die typically. Obviously, your part is gone. So there's a ton of trial and error with this, which is tricky. By the way, when you make these things to try and prevent the destruction of your dies, something I don't think people realize is you actually take this carbon die, so a graphite die, and then you wrap the inside of that die with graph foil, which is exactly what it sounds like. It's graphite foil, really thin stuff. You roll it real flat, and then you have to cut it the exact inner diameter so that it fits it perfectly and doesn't have a gap or an overlap, which is way harder than it sounds.
I'm sure they have punches.
It's so tricky. No, they cut it by hand. Like you take your die, the cylinder, right, the piston, you roll that around it, you line it up, and then you cut it with a razor. At least every place I've ever been that does that. So it's
all right, listeners. This is your invention opportunity. This is how you can break out and make it big. You can make an automatic press for
it's pretty cool. Like
foil.
You put the graphite on there, and then when you want to eject your sample at the end, out comes your like tube of graph oil now, which is like partly sintered itself. It's much more brittle. You unpeel it, and there, hopefully, is a glorious, not broken sample, but it's still tricky.
It's like unwrapping a present.
It is.
The other great advantage of the SPS process is these really high heating rates. They can get up to 1,000 degrees Celsius per minute.
Yeah.
I wish the seat heaters in my car would go that fast.
or this shed.
The shed. Yeah, like it's like by the time I get to the grocery store, it's just starting to get warm. It's like, oh,
Yeah.
come on.
But that's a big advantage because think if you don't have to wait for things to heat up, or cooling down is the problem, but heating up, all of a sudden then you could control grain growth, right? You could heat up to the temperature where you get the right phase, where you get sintering, and then ideally you could quickly also then turn it off so that you're not spending any extra, you're not giving it more energy to allow the grains to grow, you're just getting sintering. So this is how you achieve nano grain structures. And this is why everyone's using this technique, because you can oftentimes, if you want to leave it a long time and grow the grains, great, you can. But it also gives you the option of turning it off and sintering it and then keeping the grains small.
And why would we want small grains?
So this goes back to scattering that we introduced earlier in the episode. So scattering, let's say you're trying to make a transparent ceramic. If you want a transparent ceramic, you can't have pores left over a certain size. It's like a micron-ish. If they're bigger than a micron, then they're going to scatter light. And then you don't have transparent ceramic. You have it just looks like a dinner plate, right? Mm-hmm. If you want to get it transparent, you've got to get those pores really small. And the grain size has to be small, like submicron. So that's tricky. You have to get all the pores out while also keeping the grain size small is not a trivial thing. That was our senior project when I was an undergraduate. I worked with a professor named Dinesh Shetty, and he gave us the challenge to make some transparent alumina. And it was so hard because we didn't have an SPS. We had a hot press, and a hot press can get it dense, but the grains grow. And so our challenge was to get it as dense as possible before we sintered it through a casting process where we had really high solids loading. It's called gel casting. And then we sintered it and just prayed our souls off that we could get this thing to keep the grain small. Again, we got it translucent. We didn't get it transparent.
Interestingly enough, there's been a number of studies to try to assess what the heating rate is actually doing, whether it's density or grain sizes. And some studies have actually suggested that the heating rate actually has a relatively negligible effect on the density, but rather it has a much larger effect on the grain sizes. Yep. So you might not actually adjust your density all that much, but for sure you're going to be adjusting the grain size.
Yeah. One thing that I like about SPS is, practically speaking, I love that you know when you're done sintering, because again, this is inside a load frame where you can probably monitor displacement. So you can see while you heat it up at first, it's expanding. So you can actually see thermal expansion. The load frame is actually getting bigger if you're maintaining the same stress on it, right? And then when it starts to sinter, you see it turn around and it goes the other way. So it starts to go negative. And then when the sintering process is done, if you keep heating it, then thermal expansion kicks back in again. So you see this like the sigmoid, like goes up, then it goes down during sintering, and then it starts to go up again. And you know you're done at that point, right? So it's actually a really cool in situ diagnostic tool that I didn't have before when I was doing pressureless sintering. You just sort of like put it in a furnace, take it out, do Archimedes density, say, dang it, I'm not even close, right? And repeat. Like this is, having that degree of process control is pretty rad.
Yeah, no, I mean, in my sintering experiments, it would be nice instead of just like,
I'm just going to try this.
Let's try 9 hours.
So other reasons why you might like small grain size, at least in field of thermoelectrics. Thermoelectrics have this really interesting challenge where you want a electron crystal and a phonon glass. You want it to be, from a phonon perspective, scatter like all the things. But from an electron perspective, you want those to just skip right through it. And that's really tricky. One of the key approaches that people have used is to try and reduce the phonon thermal conductivity through grain control, basically making grain size really small. It also does influence your electrons, but it disparately influences phonons, and so you get a net benefit with nano-sized grains.
The last thing we want to talk about is the current. There were a number of studies that showed that using current itself and the ability for current to potentially flow through your material does have an effect. By measuring samples where at different current densities, they actually saw a measurable effect. So while the direction of current doesn't really matter, the current itself does.
Gotcha.
And there have been 3 explanations to try to explain what current's doing. The first is this electron wind modification of diffusion flux that we mentioned. This is the idea that somehow mobile electrons are going to impart momentum onto ions. It really just doesn't seem to hold weight under any sort of critical thinking. And this was the prevailing notion for a little while, and it really just doesn't hold weight. I think the better one is this idea that it reduces the activation energy for defect mobility.
That's
so
much
it
more
essentially
believable.
It increases the plasticity and allows for better compaction and sintering.
So beyond thermoelectrics and transparent ceramics, there's obviously lots and lots of applications for this technique. What were some other ones, just categories that you came across while you were doing lit reviews?
Yeah, I saw a cool one where they used it to improve bulletproof armor. So think about it. They want to have a gradient structure where the surface is really hard to try to prevent bullet penetration.
But toughness in the
But they want to have
center?
toughness at the
Oh,
end.
that's
So
cool.
because they have such nice fine and control over grain structure with the SPS method, they're able to really get that nice functional gradient in their material and get good adhesion and sintering.
That's very cool. What else?
The other one was they were able to get better shape memory alloys because they had a very controlled grain structure. There was less defects in it, and so they were able to extend the shape memory alloy effect.
Very cool. Well, I've got a challenge for any listeners out there. Do you use SPS? Drop us a line. Tell us how you use it. How is it useful? Is it not useful? Did you try it and it failed? Like, we want to hear about it. So you can find us on our Instagram. If you go to @materialism.podcast, leave us a note. We're going to have a post about this. We're going to show some of the pictures of us using our tool and showing you what it's like. But we hope you've enjoyed this episode. We certainly had a blast recording it and studying it. We hope that you reach out to us with future ideas for episodes. Maybe you're at a company and you think to yourself, hey, I'd love to be on the Materialism Podcast. Even better, shoot us an email, materialism.podcast@gmail.com. We're having an increasing number of shows in conjunction with sponsors from industry, and that makes for really cool episodes. Special thanks to the people who make the music possible. Alphabot and Colite, you know who you are. Thank you so much. We love what you've done for us so far. And if we can ask one special favor, we would love it if you would leave us an iTunes review. I don't know why, but like iTunes is the coin of the realm in the podcast universe, and we're trying to break into that top 100 of the Mongolian science tech podcasts. We're going to get there, gang, but only with your help and your reviews. So dance on over to iTunes and say, it's delightful. His sultry sounds I can't wait for twice a month. Andrew's voice is just the very best. Jared cuts the audio with precision and beauty. 5 out of 5 stars. Okay, thank you so much. We can't wait till next time. We'll talk to you soon.
See ya.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.